All right, for homework number 10, the first problem says write the next two apparent terms of the sequence. Describe the pattern used to find these terms. So they don't want you just to say I multiplied by negative 1/2. They want you to come up with the nth term for that. So looking at what do you do to get from one term to the next? If you're not sure on this, you can try dividing consecutive terms like -3/2 divided by 3. But if I look at this, it looks like I multiply by -1/2 to get each term, right? If I multiply -3/2 times -1/2, I get +3/4, and that's just going to keep working. So I'm going to just use that idea to get the next two apparent terms. So -3/8 times -1/2 is +3/16. And then that times -1/2 is -3/32. So these are the next two apparent terms. And even though the pattern is like, okay, multiply each term by -1/2, how do you get these specific terms? So looking at this, I have n equals 1, n equals 2, n equals 3, and 4. I want to try to come up with a pattern that generates these terms. And I could use, this is 5, this is 6. So keeping that in mind, I want to connect it, like the denominator. It looks like the denominator is our powers of 2, but they're like one behind. So the second term is 2 to the first. The third term is 2 to the second. The fourth term is 2 to the third. So this could be like 2 to the n minus 1. And then there's always a 3 in the top. But sometimes it's -3 and sometimes it's +3. So I think we could say 3 and then there's a -1. It can't be to the n because then all the even terms would be positive and all the odd terms would be negative. But if we make this n minus 1, just to kind of match the two, that would make this -1 to the 0 is 1. -1 to the, when I plug in 2, I get -1 to the first, which is negative. So that's going to work. And then I would clean this up. Like both of these are to the n minus 1 power. So we could really just say we have 3 times, you could just make this -1/2 to the n minus 1 power. And that would give you that pattern. So that's sort of our nth term is our pattern for this one. All right. For this one, determine the convergence or divergence of the sequence given the nth term. If the sequence converges, find its limit. So when you're determining convergence or divergence, you can just start right away with taking the limits as n approaches infinity. My pen's not working very well today. There we go. So you could break this up if you want to, 1 over n squared. Or you can leave this. I think I'm going to leave this one. I split it up in homework number 9. But let's just look at this. What if we just leave it all together? So the top is either going to be 1 plus 1 or 1 minus 1. So the top is either going to be 0 or 2. But that part doesn't matter because the bottom is going to be infinity. So we're going to get 0 either way. So if the sequence converges, find its limit. So this is the limit. And this also tells me that a sub n, the sequence converges. The sequence converges to 0. That means the terms are approaching 0. Okay. Determine whether the sequence with the given nth term is monotonic and whether it's bounded. Use a graphing utility to confirm your results. I guess I didn't do that. I realized I did not read that part when I did the directions the first time. So I'm probably not going to confirm with my graphing calculator, but if you want to, change your mode to sequence mode like this. Type in whatever you're looking at. So 4 minus 1 over n. And then you could just hit graph and see if it seems like your boundaries are correct. I'm not going to bother with that though. So, okay, is the sequence monotonic? Is it always increasing or always decreasing one of those? Start by just generating some terms. That's what I always do. I don't want to get too technical with it. I just want to see if I plug in numbers and they are decreasing right off the bat, then that'll help me figure that out. So when I plug in 1, I get 4 minus 1 is 3. When I plug in 2, I get 4 minus 1/2, so 3.5. Plug in 3, 4 minus 1/3 is 3 and 2/3. So far these numbers are increasing, right? I'll plug in one more. Plug in 4. 4 minus 1/4 is 3 and 3/4. So yeah, the fraction is just going to keep getting closer and closer and closer to 1 because we're subtracting less and less. So this is eventually going to approach 4 minus 0, which is 1, which is 4, sorry. So this is definitely a monotonic. So A sub n is, I really don't know why this isn't writing well. Okay, sorry. Put it over here. A sub n is monotonic. And in this case, it's monotonic because it's strictly increasing. I can see the lower bound right here. This the terms will never get back to 3, so that's the lowest term possible. And there is a ceiling to where they hit. I find the upper limit by saying, or the upper bound by taking the limit as n approaches infinity of this increasing sequence. So I get, when I do that, 4 minus 0, which is just 4. So that is the upper bound. All right, so yes, this is monotonic. Yes, it's bounded. The lower bound doesn't matter. If the sequence is increasing, it's the upper bound that matters. It's increasing and it hits a ceiling. If the sequence is decreasing, then it's the lower bound that matters. So you don't have to be bounded top and bottom. All right, so for this one, let's just generate some terms first. So if I plug in 1, I get 1 over 2 to the third, 1/8. If I plug in 2, I get 2 over 2 to the fourth, 16. So that's 1/8 again. Sorry, I'm really having pen issues here. It's frustrating. Okay, 1/8, 1/8. If I plug in 3, I get 3 over 2 to the 3 plus 2. 2 to the fifth is 32. 3 over 32. If I plug in, let's do one more. Plug in 4. And I get 2 to the 6th, 4 over 64. Now, it might be kind of hard to tell. Well, obviously, the first two terms are not decreasing. This stays the same. But then what's happening in the long run? Because sometimes it will be that the first couple of terms either stay the same or maybe even increase and then decrease. But again, we're looking at, do the terms approach a single number? So it's really just the long-term behavior. As long as this doesn't fluctuate up and down, we can still call it monotonic. So this is getting smaller, right? 1/8 is like 4 over 32. So you go from 4 over 32 to 3 over 32 to 2 over 32. It's just going to keep getting smaller, right? So A sub n is monotonic. Although I'll just say like after term 2. You can say something like that. And then there is a bound here too. So this is a decreasing sequence. The terms are getting smaller. So I want to look at the lower bound. So the limit as n approaches infinity of n over 2 to the n plus 2. So a linear over an exponential is definitely going to come out to 0. And so that is the lower bound. All right. Next one is negative 2/3 to the n. So if we generate some terms here, A sub n. So if you plug in 1, you get negative 2/3. If you plug in 2, you get 4/9. If you plug in 3, you get negative 8 for 27, etc. So this is not monotonic because the terms are not strictly increasing or decreasing. They're going back and forth. So something that's alternating like that can't be monotonic. So not monotonic. It doesn't mean the sequence and the terms are not approaching a number. It just means it's not monotonic. This is bounded. There is an upper bound. What's the highest number this is ever going to be? The highest positive number should be right here because we do know that as we let n get really large, this fraction that's less than 1 is going to approach 0. So the largest positive number is that first one right there. So there's an upper bound of 4/9. There is a lower bound. The lowest number, the farthest from 0 that it will ever be, is negative 2/3. Now, I'm only showing you both bounds on this one because it's not monotonic, so it's not like one has more importance than the other there. I'm just answering that question. And I could answer the upper and the lower for any of these too. I probably did on my answer key. So 93 is the same thing, but not alternating. So these terms are going to be 2/3, 4/9. This pen is driving me crazy. 4/9, 8s, 27ths, 16, 81st, etc. So this is monotonic. The terms are decreasing. And there is an upper, which is 2/3, upper bound, but there's also a lower bound. The limit as n approaches infinity of 2/3 to the n, because that's a fraction less than 1, between 0 and 1, I should say. That limit is 0, and that's the lower bound. For number 94, now they've flipped the fraction. Now it's 3/2. So a number larger than 1, as you raise it to a power, it's just going to keep growing. Think about compound interest. So this is definitely an increasing. I don't even need to list out the terms. This is monotonic. You're going to get 3/2, 9/4, 27/8. It's just going to keep growing. So monotonic, increasing. There is a lower bound, which doesn't matter, but there's a lower bound, 3/2, and then it only gets larger from there. So there's no upper bound. So that means we can't find the limit. The limit would be infinity as n approaches infinity. Okay, for this set, it says use theorem 9.5. That's the one that says if you can show that a sequence is bounded and monotonic, then the sequence converges. I still think this theorem is kind of silly for our purposes because if we use this theorem to say something converges, then the question is, well, what does it converge to? You still just go back to taking limits like we learned yesterday. So it's not that helpful in my opinion, but just in case it's on our AP test, we'll just take a look at it. So use the theorem to show that the sequence converges, verify that with a graphing utility. Okay, so I want to show that the sequence is monotonic, so I'm going to list out some terms here. So if I plug in 1, I get 5 plus 1 is 6. If I plug in 2, 5 plus 1/2 is 5.5. Then if I plug in 3, 5 1/3, 5 1/4, etc. So that's enough to convince myself that A sub n is monotonic. This pen, okay, is monotonic, decreasing. Sorry, this is messy. And I only care about the lower bound because this is decreasing. So the limit as n approaches infinity of 5 plus 1/n will work out to be 5 plus 0. And that is just 5. That's also the lower bound. So yes, A sub n converges, and I know it converges to 5. The theorem just tells me converges. My limit tells me converges to 5. And I graphed it over here, verified. Okay, for 102, same idea. I'm going to list out some terms first. So if I plug in 1, I get 4 plus 1/2, which is 4.5. If I plug in 2, I get 4 plus 1/4, which is 4 1/4. If I plug in 3, I'll get 4 1/8, etc. So that's enough to tell me that A sub n is monotonic. It's decreasing. And there is a lower bound. I'll just go ahead and show my limit notation to prove it here. The limit of, as n approaches infinity, of 4 plus 1/2 to the n is 4 plus 0, or 4. And so that means that A sub n converges by the theorem. It's bounded and it's monotonic, and it converges to 4. Okay, the rest of these I left my written answers on. I just wanted to talk through them a bit. So 103 says let sequence A be an increasing sequence such that the terms fall between 2 and 4. Explain why the sequence has a limit. What can you conclude about the limit? So if A sub n is increasing, that means it's monotonic. And we see that there's an upper bound. The terms will never exceed 4. So that fits theorem 9.5, which means that the sequence converges. And then what can I conclude about the limit? Because this is an increasing sequence and the upper bound is 4, I can conclude that the sequence converges to 4. 104 says A sub n is a monotonic sequence, so it fits the monotonic part, such that the terms are less than or equal to 1. Discuss the convergence of sequence A sub n. If it converges, what can you conclude? So they did tell us that A sub n is monotonic, but they didn't tell us in which direction, whether it's increasing or decreasing. So I can't really make a conclusion, but I discussed anyway. So if A sub n is increasing, if that's the type of monotonic increasing, then there is a ceiling. There's an upper bound of 1. The terms will be less than or equal to 1. So that means that the terms would converge. If A sub n is decreasing, then there wouldn't be any lower bound because it doesn't say that there's a stopping point. A is just, the terms are just less than or equal to 1. So this could continue to decrease to negative infinity. So that means the sequence would diverge. Okay, 107. Is it possible for a sequence to converge to 2 different numbers? If so, going to give an example. If not, why not? So no, because remember, convergence means a sequence that converges means that the terms are approaching one single number, so not 2 different ones. 108, in your own words, define each of the following. So see, what is a sequence? When we list out a sequence, it's really just a list or a string of numbers, right? Like just list these numbers out. It doesn't say to add them or subtract them, or it's just here's a list of numbers. So I said a sequence is a list of numbers given by some sort of pattern. What is convergence of a sequence? Kind of what I said in 107. The terms are approaching one single number if a sequence converges. A monotonic sequence means that the terms are strictly increasing or strictly decreasing. Or I guess it's really kind of in the long run, though, like if the first 1 or 2 terms are not increasing or decreasing, and then the rest has different behavior, it could still be monotonic in the end. A bounded sequence is just when you have a max and a min value, basically, for your sequence. And then 109, which one of these is a sequence with alternating signs? So you can see the terms have to alternate every other from positive to negative, and that happens in the first graph. It does not happen in the second graph. So the first one has to be an alternating sequence. The second one is not. All right, that finishes this assignment. Hopefully this was kind of short. This theorem is a strange one. I have not seen it all over the AP test, but it's good to know about and think about as we get further throughout this chapter.